Hello, this is our presentation for where we are and what we're looking at, query-based worldwide image geolocalization using hierarchy and scenes. I'm Brandon Clark, and this paper is co-authored by Alec Kerrigan, Parth Kulkarni, Vicente Cepeda, and Dr. Mubarak Shah. As a quick preview of our paper, we're the first transformer decoder-based architecture to solve the worldwide image geolocalization problem. We extract different features for each hierarchy and scene by using geographic queries. We propose a new testing dataset with real-world images and reduce geographic biases that are found in existing testing sets. And we improve location prediction on existing datasets by as much as 40%. Here we can see our overall model diagram, which I'll go over in the coming slides. So we see that the start of our architecture, given a query image, we project it to patches and then send it through a SWIN transformer encoder. Then we have the decoder queries or hierarchy queries. Each query is tasked to extract specific features from an image. We have 7 hierarchies and 16 scenes, which leads to 112 queries overall. They're all of size 1024. They're randomly initialized, and this 0th channel is trained to be the scene confidence. So here we can see we have our scenes, forest, cultural, industrial, and so on. And then we have our 7 hierarchies with that 0th channel, which I'll go over later. These queries are passed into our hierarchy independent decoder, which extracts image features via cross-attention. This is a normal transformer decoder using multi-head self-attention, layer normalization, and feed-forward networks. So I'll move on to our hierarchy dependent decoder. So after all of our queries have gone through the independent decoder, they're passed into our dependent decoder here. And what this dependent decoder does is it allows the queries to specify which hierarchy they represent by having the self-attention and feed-forward network layers be specific to each hierarchy. So if we look a little bit closer, when the queries come in here, during the intra-hierarchy self-attention step, only the queries that are looking at hierarchy 1 will perform self-attention among themselves, and then the queries that are responsible for hierarchy 2 will perform self-attention among themselves without any crossing between hierarchies. The same is true for the feed-forward network stage. All of the queries for hierarchy 1 are passed through their own feed-forward network, and all the queries for hierarchy 2 are passed through their own network, and so on. Here we see the main difference in the equations for this dependent decoder is that each geographic query is denoted by the hierarchy that they represent. For scene selection, what we do is we average the 0th channel among all of the queries for a specific scene. And the highest value is selected for that scene. So we can see that for the forest here, we take all of the queries that represent a forest, average the 0th channel to get one value, do that for every single scene, and then the most confident one is selected to go on to classification, and we have a cross-entropy loss to enforce scene prediction. Once we've picked which queries we want to pass into the classifiers, they come down and each query goes to a classifier specific for their hierarchy. When we're doing the testing, each prediction is combined to make one refined final prediction, and all of our predictions are passed through a cross-entropy loss to help enforce the accuracy. We can see that our coarsest classifier has 684 classes, and our finest classifier has 21,000 classes. For training, we use the Media Eval Places 2016 dataset, commonly called MP16. It's around 5 million images with GPS coordinates from Yahoo and Flickr. It's a subset of YFCC 100 million, and it's uncurated. And here we can see the distribution of that data set. For testing datasets, we use M2GPS, which is about 300 images, and M2GPS 3K. These are curated datasets of landmarks, which we see at the bottom. And then we can also see the distribution here of these testing sets. It's mostly located in North America and Europe, with some images in Eastern Asia. We also use 2 versions of the YFCC datasets, YFCC 4K and YFCC 26K. These are uncurated datasets that are also a subset of YFCC 100 million. And we see they have a similar distribution where they're mostly in North America, Europe, and a small amount in Eastern Asia. For our data set, we wanted to solve those distribution issues that we saw with the previous testing data sets. And we also wanted to make sure that all of the images we got were real world geolocalizable images. So what we did was we took images from Google Street View. To do this, we picked a country with a probability based on the surface area on the Earth. We picked a town or city within that country, and then picked a random coordinate within 5 kilometers of the town or city. What this gave us was a good sampling of images that were geolocalizable and relatively evenly distributed about the Earth. For results on IM2GPS, we see we got state-of-the-art on every distance metric from 1 kilometer up to 2,500 kilometers. For IM2GPS 3K, we got state-of-the-art on 1 kilometer, 25, and 750, but fall just short on the 200 kilometer accuracy and 2,500 kilometer accuracy. For YFCC 4K, we got state-of-the-art by about 2% on 1 kilometer and by about 8% on 2,500 kilometers. And for YFCC 26K, we got state-of-the-art by about 3% on 1 kilometer and almost 9% on 2,500 kilometers. For our Google World Streets dataset, we showed results on translocator, which only got 0.5% accuracy on 1 kilometer, where our dataset got 0.7% accuracy. We can see that this dataset is a lot harder than pre-existing datasets, which I think is due to the distribution and making sure that all of our images were real-world images. We show some qualitative results here on an image from IM2GPS 3K. We can see the attention map for every single query based on their scene and hierarchy. And we see that our queries are learning different sets of features for every single hierarchy. If we look at this first column here, each one is looking at slightly different aspects of the image. And we can also see that as we get less confident in our scene prediction, the query starts to look at more random areas of the image and is getting less information. In conclusion, extracting features unique to each geographic hierarchy is important for geolocalization. Our model shows significant quantitative improvements, and our qualitative results show that the model works as intended. And our new testing dataset solves limitations of the other test sets while also showing the limitations of the problem of geolocalization in general. Our code is available at this GitHub here, and here are our references. Thank you so much.